I used momentum, not necessarily conservation of momentum, but momentum nonetheless. So I have that the initial momentum p at time t is just mass times velocity of the raindrop. And then after a little bit of time dt, the momentum is mass plus the small amount of mass that it gained times velocity plus the small change in velocity, which could be either positive or negative, which would most likely be negative. And then foiling that out, I get these terms, and this dm dv is so small we can just neglect it and call it 0. So I get p at time t plus dp is this equation. And then, so we know that the net force is equal to the change in momentum over the change in time. And then since the raindrop is falling towards the earth, you have the force of gravity acting on it. So m times g equals dp dt. And plugging all of that in, that simplifies to mg equals mv prime plus vm prime. And then I substituted the equation that we have for mass with respect to time, substituted that, put it in Mathematica to solve for me, and I got this equation for velocity. And then solving for the constants, I just said that v at time 0 is v naught. So c1 equals v naught times m naught, so this is our final expression for velocity. Now, if k equals 0, then no mass is gained. So it's just your standard free fall problem. So you get v of t equals gt plus v naught, and to test that I just use kinematic equations. You know that this is the equation for y. If you take the derivative with respect to time, you get velocity, which is the same as gt plus v naught. And then also acceleration is the time derivative of velocity, which is just g, which works. Yay!